Sometimes, when our independent variable approaches a point like a, the function goes to infinity. And sometimes, when we approach infinity, our function gets closer and closer, infinitesimally to a certain point like a. These are infinite limits, and these are limits at infinity. In the first part of this video, we are going to see a lot of examples to see how we can find these kinds of limits. And in the second part, we are going to take some time to see their exact epsilon-delta definition, which is the formal definition of these two kinds of limits. Our first example is the limit of the reciprocal of x when x goes to 0. For a limit to exist, the left-hand limit and right-hand limit must both exist and be equal. This is how we can write the right-hand limit. 1 is a positive constant, and this is a very small number that tends to 0 through values arbitrarily close to but greater than 0. So this limit is plus infinity because 1 divided by positive 0, which is not actually 0 but a number very close to 0, gives positive infinity. In fact, it yields infinity because any constant you choose is infinitely larger than positive 0 you see here. Now try to think about this limit when we approach 0 from the left. Here, a positive constant divided by negative 0 takes us to the negative side of infinity. It's simple. Positive divided by negative always gives negative. So these two limits are not equal and the limit does not exist at this point. You can clearly see on this graph that as we arbitrarily tend to 0 from the right, the graph goes to infinity, and by approaching 0 from the left, the graph goes to minus infinity. This is the vertical asymptote of this function. The line x equals a is a vertical asymptote if at least one of these conditions is true. Either by approaching a from the right, the function goes to infinity, or by approaching a from the left, the function goes to plus or minus infinity. Now, as our next example, let's talk about this limit. The right-hand limit is positive infinity because the 1 positive to the power of 2 you see in the denominator is still infinitesimally larger than 1, and the result is a positive 0 in the denominator. For the left-hand limit, 1 minus to the power of 2 is still smaller than 1. Imagine a number like, for example, 0.99. If we take it to the power of 2, it is still smaller than 1. Even smaller than itself, because when we multiply numbers that are smaller than 1 with themselves, they yield a smaller number. So this limit does not exist. But there is a vertical asymptote at x equals 1. You might also be curious to find this limit because it's another point that takes the function to infinity. So let's check it. This is the right-hand limit, and we need to pay attention to minus 1 positive in the denominator. As you can see in this picture, as we approach minus 1 from the left, we are dealing with a number like minus 0.99, which its absolute value is smaller than the absolute value of minus 1, and also its square is smaller than the square of minus 1. So at this point, x squared is smaller than 1, and the limit goes to minus infinity. On the other hand, when we approach minus 1 from the left, the square of this arbitrarily close number is larger than 1. So the denominator is 0 positive and the limit is positive infinity. Again, the limit does not exist. And we have another vertical asymptote at x equals minus 1 here. This is the function we have been talking about, and these are the two vertical asymptotes as our limits suggested. In the case of this function, you can visually confirm that the limit exists, because the right-hand and left-hand limits exist and are equal. In fact, for both denominators, 0 positive and 0 negative are two very small numbers that, when squared, become even smaller and positive. So this limit exists and is equal to plus infinity. Now let's find the limit of tangent as x approaches pi over 2. Again, we first try to find the right-hand and left-hand limits, knowing that tangent of x is sine of x divided by cosine of x. The best thing you can ask for here is a unit circle to visualize how x is getting closer and closer to pi divided by 2. Pi over 2 negative means that we are talking about angles smaller than 90 degrees. In other words, we are talking about the first quarter. Pi over 2 plus, on the other hand, means that we are talking about angles that are arbitrarily larger than 90 degrees. In terms of quarters, we are on the second quarter. In the first quarter, it's clear from the unit circle that sine of x is approaching 1 as x approaches pi over 2, and also cosine is getting closer to 0 by positive numbers. Similarly, in the second quarter, sine of x is approaching 1 again, but cosine of x tends to 0 by negative values. So, for the second limit, which is happening in the first quarter, tangent is approaching positive infinity, but for the second limit, which is in the second quarter, our function is approaching negative infinity. Again, unfortunately, the limit does not exist, but at least we have a vertical asymptote, and I really don't know why I said unfortunately, because it is how it is, and it doesn't matter whether we have a limit or not. Anyway, actually, if you take a look at the graph of tangent, you will see that not only it has a vertical asymptote at x equals pi over 2, but also at infinite other points on the graph, as you can see. The next two functions we are going to talk about are natural exponential and natural logarithmic functions. We know that ln of x is the inverse of e to the x, so the range of the exponential acts as the domain of natural logarithm. More specifically, the range of this function is all the positive numbers, and e to the x cannot be negative or 0 because we can't find any value of x in real numbers, so that e to the power of the function becomes 0. That's why x cannot be negative or 0 in this function, and limit of 0 from the left is meaningless for natural logarithm. But we can investigate the limit as x approaches 0 from the right. Now let's see how we can handle this one. When we say x is approaching 0 for ln of x, we can see it as e to the x is approaching 0 from the right. This only happens when x is a very large negative number, which is denoted by minus infinity. So in the case of natural logarithm, ln of x must go to negative infinity as x goes to 0 from the right. This is because the range of exponential function is related to the domain of the natural logarithm. Take a look at these graphs. This function is e to the x, and this one is its inverse, which is ln of x. You can see that approaching 0 from the right in the domain of natural logarithm is similar to approaching 0 from the right in the range of the natural exponential, because they are inverse functions. As our last example of infinite limits, let's take a look at this one. We have two quadratic equations in the numerator and denominator. We can simplify both the numerator and the denominator by factorization. One of the x minus 2's in the denominator can be eliminated by the same term in the numerator, and now we can deal with this limit. The limit from the right is a positive number a bit larger than 2 divided by another positive, which is really close to 0, so the limit is positive infinity. And for the limit from the left, we have a positive number slightly smaller than 2, which is positive, and a negative small number close to 0 in the denominator, and the limit is negative infinity. This is the graph of this function, and this line is the vertical asymptote of this function, but the limit at this point does not exist. Now it's time to talk about limit at infinity. It means that we want to know how the function behaves when we approach very large numbers, larger than any number you can imagine. Our first example is 1 over x. For every large number, the function tends to 0. We can also take the limit when it goes to negative infinity, which is another limit, and again goes to 0. This is the graph of this function. The line y equals 0 is called a horizontal asymptote. A horizontal asymptote is a horizontal line with the equation y equals a that when x goes to either plus or minus infinity, the function gets infinitesimally close to this line. Our next limit is a rational function. There is a degree 1 polynomial in the numerator and another degree 1 polynomial in the denominator. At very large x, x plus 1 and x minus 1 can be treated as x because minus 1 and plus 1 would be very small in comparison with x and the limit becomes 1. This also applies for the limit when x goes to negative infinity and the result is again 1. As you can see in the graph of this function, there is a horizontal asymptote at y equals 1. What about this one? The order of the polynomial in the denominator is higher in this case. At very large numbers, this limit can be written as x over x squared, and it's clear that the limit goes to 0. You can see in the graph that both infinite limits go to 0 because the polynomial in the denominator dominates and take the limit to 0. But pay attention that when x approaches negative infinity, the function tends to 0 with negative values, and for positive infinity it tends to 0 with positive values. When we have a rational function with two polynomial functions in the numerator and the denominator, if the degree of the p of x is larger than q of x, the limit goes to either minus or plus infinity based on the leading coefficients. If they have the same degree, the limit is the leading coefficient of the numerator divided by the leading coefficient of denominator. And finally, if the degree of the polynomial in the denominator is larger, the limit goes to 0. The next example is arctangent of x. We are going to use the unit circle to calculate the limits. This axis is the tangent of x, and for the arctangent function, the value on this axis is the value of x we use in the inverse function. When the values on this axis get larger and larger in the positive direction, the value of arctangent tends to pi over 2. And when x goes to minus infinity, the limit of arctangent becomes minus pi over 2. This is the graph of arctangent of x, and you can see that the limits at infinity are pi over 2 and minus pi over 2. Now, what about this function? The numerator is a degree 2 polynomial under a radical, and the denominator is a degree 1 polynomial. What do you expect the limit to be? If we divide the numerator and denominator by x, the numerator becomes the square root of 3 plus 1 over x squared, and the denominator becomes 7 minus 3 divided by x. We can write the limit like this, and by taking the limit under the square root, we are assuming that the limit of what is under the radical does not become negative. This is 3, this limit is 0, this one is 7, and this is also 0. So our function tends to a square root of 3 over 7. For negative infinity, finding the limit gets a little tricky as we are dealing with a square root. We can write the expression under the square root as x squared multiplied by the other term, and when we take it out, we must write it as the absolute value of x. Now let's rewrite the limits. As we are dealing with negative values, the absolute value of x becomes minus x and a negative sign appears here. So the value of this limit becomes minus a square root of 3 divided by 7. Our function has two horizontal asymptotes. One of them is this and the other one is this. And pay attention that the function is approaching the asymptote from the right with negative values larger than minus the square root of 3 divided by 7 here. Next example, what should we do with this one? We are dealing with the case of infinity minus infinity. It's not easy in this case to find how this function behaves at infinity. We can multiply this function with this fraction which leaves 1 in the numerator and the term you can see in the denominator which clearly goes to infinity because it is the sum of two infinities. So the limit is 0 because it is 1 divided by a very large number. Pay attention that as x goes to negative infinity, the function goes to infinity. This is the graph of the function and the horizontal asymptote is the x-axis. The limit of ln of x as x goes to infinity is infinity as you can see. The limit of exponential is also infinity as x gets very large. But the limit of exponential function is 0 when x goes to negative infinity. Now we want to see which functions grow faster at infinity. This is the order of growth of some of the most important functions you may come across. Let's see some examples. For example, this limit is 0 because x squared grows faster than the logarithmic at infinity. This is x squared, and this one is the logarithmic function. This one is also 0. It is clear on the graph that as x gets larger, x to the x grows faster. You might think that x to the 1000 must be very large, but this limit is also 0. We can write it in this form, in which there is a growing factor in the denominator, and as x gets larger than 1000, the function tends to smaller values and the limit is finally 0. Now let's think about this limit. We can write it as a over b to the x. If b is larger than a, the limit is 0 because the base is a number smaller than 1, and as x gets larger, the function tends to 0. If a and b are equal, we are dealing with a constant function and the limit is 1. And finally, if a is larger than b, we are dealing with an exponential with the base larger than 1, which goes to larger values as x goes to infinity. In the last part of this video, I want to talk about the precise definition of infinite limits and limits at infinity, using two arbitrarily small numbers, epsilon and delta, and also two arbitrarily large numbers, m and n. If f is a function that is defined on some open interval containing the number a, except possibly at a itself, then this limit that goes to infinity means that for every positive number m, there is a positive number delta, such that if x is in the delta distance of a, then every number the function gets is larger than number m. For infinite limits that go to negative infinity, we have the same definition, but the infinity here is negative, and we use the negative version of the arbitrary number for which the value of the function is smaller than this number for arbitrarily values of m. Now for limits at infinity, if f is a function that is defined on this interval that goes to infinity, then this limit at infinity, which yields a constant L, means that for every arbitrarily small number epsilon, there is a number n such that if x is larger than our arbitrarily large number n, then the value of our function will be in the epsilon distance of L. And again, we have the same definition for limit at negative infinity, but here we have negative infinity. And this inequality suggests that every x we choose is smaller than the negative number n, which suggests that the concept of negative infinity. And finally, if f is a function defined on this interval, then this infinite limit that goes to infinity means that for every positive number m, there is a corresponding positive number n, such that if x is larger than n, then f of x is larger than m. And these were the formal definitions of the limits we talked about on this video.